How many more papers do you have left?
I have around 20 more. I can't believe you have to sit here the entire night grading these papers.
Yeah, I wish there was some way we could automate this.
You know what, Akash? Let's do it.
Hi, I'm Akash.
And I'm Mukund. So here we are today to explain to you a system that we built. That system being the real-time automated answer scoring system.
So now we're here to walk you through the main aspects of our system, namely the dataset we use, the preprocessing we use, as well as some of the models, and share our results. Now let's get started with the dataset. The dataset we used for the project was the Hewlett Foundation's automated essay scoring dataset, which was featured in a Kaggle competition. This dataset consists of 8 different sets of essays with average essay lengths ranging from 150 to 500 words.
Now every essay over here in this dataset was graded by a human evaluator. This means that it was real-world data and that we were trying to get real-world results. Now we had around 10,686 samples, of which we divided into two parts, 85% for training and 15% for testing. We had an additional constraint as well, that being that each set in this dataset had a different grading scale. So now moving on to preprocessing and word embeddings, we use 3 forms of preprocessing. Namely, let's start with stemming. Stemming is basically tracing a word back to its root word. So for example, you have aggressive, aggressiveness, aggressor, and aggression. Now all these words would be traced back to its root word, that being aggression. Let's move on to spell correction. Now for spell correction, we use Peter Novick's very effective spell correction algorithm. Apart from that, not much to say, it's just basic spell correction.
Alright, so tokenization is the breaking up of text into smaller pieces. In our case, the pieces were words. Now, along with tokenization, we also had removal of stop words, which are basically commonly occurring words in the English language that don't bear much value to our evaluation. We also removed infrequently used words from our training data set.
So now let's move on to the word embeddings. We use 2 different types of word embeddings to illustrate the difference between your word vectors when you train it on your own data set versus when you use a pre-trained data set.
We used word2vec to illustrate training on our own data set, which was our training set, and global vectors to train on pre-trained word vectors.
Moving on to our models. So we decided to go a little basic at first, and we tried a radial basis function with a support vector machine as well as a random forest classifier. Now the results from these surprised us, which begged the question, how would it perform if we tried a slightly more complex network?
So then we went on to build our deep neural networks as well as our LSTMs. Now, LSTMs are RNNs, which basically work better with sequential data, and what better sequential data than text.
So let's move on to our results. But before we explain to you our results, I think it would make more sense if we explain to you the evaluation method that we use.
Alright. So here it is, the quadratic weighted kappa. What the quadratic weighted kappa basically does, measure agreement between two raters. It can be summarized in this formula, where W is your weights matrix, O are your observed values for each essay, E is your n by n expected histogram for the values. Now, kappa typically varies between 0 to 1, but could also go into the negatives with complete disagreement between raters. Now, why did we choose kappa over accuracy? Well, that will be further explained by Mukund.
Alright, so imagine you have 2 raters, rater 1 and rater 2, and they both are evaluating 3 essays. Rater 1 evaluates them to be 10, 9 and 1, whereas rater 2 evaluates them to be 10, 8 and 5. Now the accuracy when you compare these 2 ratings is a meager 33.3%. But does that really explain the agreement between the two? I don't think so, which is what quadratic weighted kappa does. So let's look at these 2 values here. The difference between a 9 and an 8 is just 1 scoring point, and your range is an entire possible 10. So the agreement, you could say, is pretty high, which is what quadratic weighted kappa represents over here with a rating of 0.7375.
Alright, in the competition, the highest achieved quadratic weighted kappa was 0.81. So this is what we used as our benchmark for our project.
So now we'll explain to you the results that we got. Now, as you can see, the random forest and the SVM decided to give us a really high accuracy, which surprised us. So now let's move on and explain to you the results from our slightly more complex models. So as you can see, the highest possible accuracy, or rather QWK, that we got was using an LSTM with word2vec, which was a 0.9705, which outperformed its counterpart of a glove model, which gave us a 0.9566 rating. Now the reason this happens is because word2vec is trained on our own data. Now our data was modeled around computer science, so let's take 2 example words, strings and threads. In computer science, it means a completely separate thing versus what it does in real life, which is what the glove was trained on using its pre-trained vectors.
Now, comparing the LSTM model with the deep neural network model, we can see that the LSTM model outperforms the deep neural network, and this can be attributed to the presence of a memory unit in the LSTM which can remember context of words.
Now, finally, we have a live demonstration that we'd like to show to you.
On the left is a graph that's updated at 0.66 second intervals, and to the right we have our interface, which is a web server built on Python's Flask web framework.
So here we have one answer which was graded by a human evaluator and received an actual score of 10. We're going to push it into our system in 3 batches and see how it evaluates it in real time.
So as you can see, our model has started to grade the answer. At the end of batch 1, the score is 8. At the end of batch 2, the score remains to be 8. But at the end of batch 3, which is the cumulative answer of the student, the answer evaluates to a 10.
So now we'll push the second example in one single batch. The answer was given a score of 24 by a human evaluator, and let's take a look at what our model scores it. So first it'll drop to 0 when the previous answer is removed, and finally you'll see that our answer gives us 24. Talking about our motivation behind this project, as you saw in the introduction, was basically to make the job of the teacher easier with respect to evaluation.
We also hope to possibly unearth new trends with respect to the way a student thinks and how he or she arrived at an answer, which is made possible through the real-time capability of our system.
So we hope you liked this video, and that's it from us. Thank you guys for watching.